Hello, everyone. This is the lecture for section 4.2, linear approximations and differentials. So this is the second section that we're going to have to do that deals with applications of the derivative, okay? And in particular, we're going to learn a little bit about why the notation is the way it is, okay? So in the previous section, we've already interpreted the derivative as the slope of a tangent line, right? We can use that as a pretty good approximation to much more complex formulas and functions, okay? So I'm going to go ahead and start the definition. The picture is going to be for the definition, really, okay? So let f of x be a differentiable function at x equal a. Then the linear approximation to f of x is given by this thing right here, okay? And the equation is given by this thing right here, okay? So essentially what this is basically, this is the written out version of the equation for a tangent line. That's all we're doing. So you guys know how to do this sort of already. We've just sort of broken it up into steps before. Now we actually get a freaking formula for it, okay? So let me explain how this actually works, okay? First of all, I'm going to go ahead and draw a function, right? So here's my function, right? And I'm going to go ahead and draw another line. And this time it's going to be a line, no shape. There we go. I hope it's going to be, okay. Let's go ahead and shove this up a little. There we go. Okay, so here's our line, right? So suppose we want, whoa, not what I wanted. That's what I wanted, okay. Suppose we wanted an approximation right here, right? Let me do this as a dotted line, right? This is going to be A. And this point over here is going to be B, okay? Then we know that the height of this line is going to be f of A, right? And this line right here is going to be, or this point right here is going to be f of B, right? So if we have, if this is our f of x, then this line, this L of x that I just found right here, okay, can be a pretty good approximation. And I'm going to do it in a different color. I'm going to do that point, right? Then we have an L of B. Whoops, wrong kind of B. Need a lowercase b. Okay, then we can say that this L of B is a pretty darn good approximation to f of B, right? Using this equation right here, the one that I have highlighted, this one right here. Okay. And notice all of this is based off of f prime, right? You guys see that f prime there? We're essentially using the slope of the tangent line, right? So how does this work out? Let's go ahead and do an example here. So find the linear approximation of sine of x plus 1 at x equal pi over 3. Verify my answer graphically. Okay, so this means I would be able to use Desmos to verify if my line is actually indeed tangent. Okay, so the first thing I'm going to show you guys, the first thing I'm going to point out is that A is going to be that pi over 3. A is going to be pi over 3, okay? To do the linearization, to do the tangent line approximation, we need sort of 3 things, right? A, f prime of A, and A itself, right? So f of A, f prime of A, and A itself. So we know what A is, that's going to be our pi over 3. Let's go ahead and find the next one. So we're going to need to find f of pi over 3. So f, good old regular f, right? So it's going to be sine of pi over 3 plus 1. And if you guys remember from your trig class, sine of pi over 3, that's root 3 over 2 plus 1. So we have now our f of a. So now next comes f prime of a, right? To do that, we need to find the derivative first. So let's go ahead and backtrack a little bit. Let's just find f of x, first of all, okay? That is going to be, we need to find the derivative of this. So the derivative of sine x plus 1, that's just going to be cosine of x. So that gives us f prime of a. Now we get to plug in pi over 3 into our f prime. So it's going to be cosine of pi over 3. And if you guys remember from trig, that's supposed to be 1/2. Okay, so we have all 3 bits, right? So we have a, f of a, and f prime of a. Now all that's left is to put it into our equation. So L of x, our linear approximation, is going to be f of a, so root 3 over 2 plus 1. Let me write that a little nicer. Plus 1, right? Plus f prime, 1/2 times x minus a, x minus pi over 3. And we are done. I'm going to move this down just a smidge so I can go ahead and box it away. That is it. We are done. This is our tangent line approximation to our function f of x. So this line that's in green right here should approximate this function right here really good at pi over 3. Okay, so now let's go ahead and verify that using our graphing utility. So let's go ahead and open up Desmos. So I'm going to first plug in sine of x plus 1. We know that's our equation, right? So this is going to be my f of x equal. And now I'm going to put in L of x. I'm going to put in that approximation. Okay, so it's going to be equal to square root of 3 divided by 2 plus 1 plus 1 plus 1/2. I'm going to do x minus pi over 3. Okay, so remember how I said we needed it close to, let me go ahead and change some of these things. I'm going to do pi over 6 steps. Okay, and then my y-axis, I'm not going to make it that big. I'm going to go ahead and change that to -5 to 5. Stretch it out a little bit so we can see what's going on. Okay, there we go. So remember how I said, right? This is supposed to be an approximation at pi over 3. So if we go over to pi over 3 on our graph, lo and behold, our line looks pretty darn tangent at that point. Okay. So the idea behind the linear approximation is that for points really close to pi over 3, we don't actually have to compute. We don't have to actually compute sine of x plus 1. We can go ahead and use linearization, our L of x formula, to get a nicer an approximation to that value. Okay. So what comes up next after this is some quick checks. So same process as the example here. Okay. Make sure to do the one that you're assigned, and I'll be checking these and putting them up in the notes very shortly. Okay. So let's go ahead and move on to differentials. So up to now, we know what a derivative is, right? And we've been using this notation right here for the longest time, this dy over dx, which is equivalent to f prime of x. Whichever one you want to use is fine, but we've just sort of picked up this notation, right? In particular, that dy over dx, not knowing what the heck it meant, okay? We never defined it. So this is where we're going to get to define what those are. And that, technically, both of them, the dy and the dx, are what we call differentials, okay? So let me go ahead and state the definition first of all, okay? The differential dx is what's considered an independent variable that can be assigned any non-zero number, okay? And then we define the other differential, dy, as the dependent variable that's given this definition right here, that dy is going to be equal to f prime of x times dx, okay? So essentially, both of these dx and dy, they're just variables, really, right? With dx being the independent one, you can assign any value to it, okay? And the dy is the dependent one. It depends on dx, okay? So that's the sort of textbook definition of what dy and dx are, right? What people really like to liken them to like as a very, very, very close definition of them, right, is that dy and dx are both infinitely small distances, right? Where the dy variable, right, that's what we call the vertical distance. So it's a very infinitesimally small vertical distance, okay? And that dy is dependent on the infinitesimally small horizontal distance dx, okay? So that's why we sort of write this. So we know that delta y over delta x from your pre-calc, that meant change in y over change in x, right? We sort of changed that in calculus to dy over dx. Notice that throughout our whole study of calculus, when we talk about limits, right, we were talking about very, very small increments. Hence the reason why we call dy dx, we liken them to infinitely small distances. And this is also why we say dy dx, oh, that's the slope of the tangent line, because we're technically approximating a slope using very, very small distances. Okay, so now I'm going to zoom out a little bit so we can get all these formulas on the screen here. There we go. Okay, and let me go down a little bit so I can put these all together. Okay, yeah, there we go. Okay, so we know that these equations we know that f of x is approximated by this equation right here. And as a much more cruder approximation, we have the linearization, right? The L of x, that formula, right? So what we're going to do now is we're going to analyze both of these formulas, okay, with specific values. In particular, we're going to look at when x is equal to a plus dx. Okay, so I'm going to copy to the best of my ability, I'm going to copy the graph that I did up above. Okay. Whoa, come on. There we go. I'm going to copy the graph that I did up above. I'm going to try at least. There, and then I'm going to grab this, and there we go. Something like that. There we go. So let me move this down again. Okay. So let's pretend, right? Let's make believe, right, that this approximation is good for here. That's what I wanted to show you guys. So let's say this is A. We know that this is going to be, right, some f of A, right? Okay. Now what I want to do is this. I want to go ahead and I'm being overly exaggerating here. I'm going to do a dx. I'm going to do an infinitesimally small distance. Try saying that 3 times fast. So that means that this point right here is a plus dx, okay? So then that means that this point right here is f of a plus dx, okay? Nothing fancy yet, okay? But here we go. So we're gonna take a look at these equations now, right? These right here, okay? But we're gonna go ahead and look at them now, plugging in x as a plus dx, okay? So if you notice, let me do this, there we go. F of a plus dx, right, is still f of a plus f of a prime, f prime of a. This is what's gonna sort of reduce down to something, right? So it's gonna be a plus dx minus a. So the a's cancel out. Notice that that's happening in both the top and the bottom. So then I have a and a minus a. So those go away. Those end up canceling. So I get left with just dx in that parentheses right here and here. Okay? Which means that we have this result here, that f of a plus dx is approximated by f of a plus f prime of a times dx. Okay? Equivalently, if we use the linearization, the L of a plus dx, right, is equal to f of a plus f prime of a times dx. Now, I want everybody to notice this thing at the very tail end right here. F prime of a times dx is in both of them. We just defined that way up here. You guys see that up there, right? So in both of these are dy's. We end up getting this right here. Okay. Since L of a plus dx is basically this point right here, I'm gonna, bam, right there. So we're saying that this is L of a plus dx, right? That is equal to basically f of a. I'm running out of colors here. So this right here is f of a, right? Plus our distance dy. So this right here is our dy. This is the difference between our actual function and its approximation. Okay? That's what we got. So now, why are we looking at this? So it turns out with all of this, we can go ahead and compute an error. How far off is our answer? Okay, that's what we can do. We can compute how far off is an answer, right? So, and more importantly, we can go ahead and use our approximation to find values that are close by. So let's say we wanted to find the approximation to sine of x plus 1 at pi over 3 plus 0.1. So this is, notice how it's a plus 0.1, so it's plus a little bit, okay? This right here is our a plus our dx, okay? And we want to determine the amount of error in our approximation. So let me zoom in again. There we go. So the first thing I'm gonna do, I'm gonna write it down here. L of x, I'm gonna grab my linear approximation from up above. This we computed to be √3/2 plus 1 plus 1/2 x minus pi over 3, right? So according to our approximation formulas that we just figured out, right? We have now L of a plus dx, that's going to be our pi over 3 plus 0.1, right? Is going to be equal to f of a plus a dy, which is equivalent to f of a plus f prime of a times dx. Okay, so this is going to be equal to, now it's just plug and chug, √3/2 plus 1 plus 1/2 times, dx, we know is 0.1. And if you compute this outright, you should get 1.9160. So our linear approximation, our L of x, right, should be off of our actual value by this much about. So it's off by 2, right? Now, you guys are probably looking at this as like, it's off by 2. That's still a lot, right? Notice that I did by 0.1, right? If I made this smaller, this error will also get smaller. Okay, and that's the real strength about all of this, that we can now make approximations, right? And then compute how far off our approximations are. Okay. Next thing that comes up is quick checks. Go ahead, do the one that's assigned to you. So the concepts that we just worked on, the linear approximations, the differentials, turns out that is like the basics, the absolute basics of whatever any computer does sort of worldwide, okay? A computer is pretty good at squaring, cubing, adding, subtracting, multiplying, dividing. It's really good at doing all of those things, right? It doesn't entirely know how to take a derivative unless you program it to do so. And those programs are very, very long, very, very complex. So what a computer tends to do is it gets, it approximates as best it can using linear functions. It uses linear functions to do approximations. Okay, unfortunately, doing calculus, having a computer do calculus can't be done yet. Calculus still needs a human brain. Okay, so that's the point behind all of these linearization applications, that computers instead, what they do is they find these linear approximations, right? And get an answer that's close enough given a pre-programmed tolerance. So it knows, like, if it's, you know, if the number is less than 0.01, it'll stop. It'll say that's good enough. I'm going to take this as my approximation, and we know it's going to be off by a certain amount. That's the cool part about this. Okay, we'll learn a little bit more about how this is working out, how this works out in a computer's brain when we get to section 4.7, I think. No, 4.9, which is what's called Newton's method. Okay. So then the last thing I want to do for this section is sort of see how useful this is, at least in sort of the physical world. Okay. So the radius of the ball bearing is measured to be 0.7 inches. Okay. If that measurement is correct, if we can determine that measurement is correct to within 0.001 inches, how far off is our volume going to be? Okay, all of this just needs sort of a little basic idea of the differential and then some derivatives here and there. Okay, so we know that, let's say the ball bearing, but let me draw a picture of what we're doing here. Here's our ball bearing, right? We know that this ball bearing has a certain radius. This is going to be an R, right? And the volume for this ball bearing, we've already seen the volume of a sphere already. This is going to be 4/3 pi r cubed. Okay. Okay. So first thing I want to do is I want to define a couple things. I want to define a dV, right? This is going to be an infinitesimally small amount in volume, right? And then we need to define dr, okay? This is an infinitesimally small in radius. Okay, so we have a dV. It's an infinitesimally small amount of volume, right? And then we have a dr. It's an infinitesimally small length in my radius, okay? So what I'm going to do here is just, first of all, I'm going to take that volume. So a volume, right, which is in terms of r in this case, is 4/3 pi r cubed, okay? I'm going to take the derivative of v with respect to r. So what I'm going to do is this. I'm going to do dv over dr. Okay, and if you guys recall here, this is going to be 4/3 pi. These two are numbers, so they get to come along for the right. And then something cubed, the derivative of something cubed is going to be 3r squared. Okay. So now this is something that I think you guys have not seen before. I'm going to separate the dv and the dr. So dv is equal to, and this people will tell you once you transfer over, you can't do this, but technically it is what it is. We are sort of semi doing it. I get to multiply both sides by the dr, and I get left with, so the dr cancels on the left-hand side, dr gone, dr gone. I get left with dv is 4/3 pi 3r squared times dr. Okay, but notice what we have here, right? Our infinitesimally small amount of volume, right, is completely represented by some multiplier times our infinitesimally small length in radius. So we are able to find how far off our volume is completely from how far off our radius is. Okay. At this point, we're basically done. It's plug and chug. Okay. We know that our radius is 0.7 inches, right? And our dr, the amount we are off, is the 0.001. So dv 4/3 pi times 3r, that's our 0.7 squared, times dr, the amount we are off, 0.001. Okay, and if you plug this all in, we get dv is equal to 0.00616. So E is off by 0.00616 inches cubed. It is off by 0.00616 inches cubed. So what did we just do here? We were given two values here. We were given the radius of a ball bearing, okay, and how much off that measurement of a ball bearing could be, right? And based off of those two things, we were able to find out how far off our computed volume would be. How far off our computed volume would be. Okay, this is super useful if you need to have a volume that's got to be within a specific tolerance. If the ball bearing's too big, you can't use it. If the ball bearing's too small, you can't use it, right? So what's the nice spot? How far off are we really? And this is it, okay? This is it, I think. After this is lecture questions. It's a short section, so not too big. Just, this section is going to have a lot less spot for arithmetic and algebraic mistakes. Still, though, keep a track of it. If this is still not making any sense, come visit me at my office hours, in the math lab, in my Zoom room. We can set up something separately, or we can talk through email or through discussion posts, okay? Besides that, I'll see you guys around. Study hard.